Hi everybody, welcome to Algebra 2. So this is our second set of videos for this week, and I apologize. We're a little bit behind schedule. There's been a flood at my house and all sorts of fun things going on. We're trying to clean up, and so I apologize that you're getting it in segments this week. So I apologize. And I'm still wearing glasses. The beautiful flowers that I've been working in that I love so much don't love me. So I look a little bit different without my contacts. So still a crazy math lady, still love algebra, just a different look. So thanks for being patient with me, and I do apologize. But let's jump into Algebra 2, Saxon. Remember, we're in our third edition, and we're looking at lesson 117 today. So lesson 117 talks about the symbols for sets and also set builder notation. Every curriculum looks at things a different way. The great thing about math is a universal language that no matter what country you're from, we have to speak that language, right? So 2 + 2 is always 4. But there are some ways that different curriculums will show those, and I really like the way Saxon does that and the cohesiveness that they have in this type of in our Algebra 2 book. It also is continuous throughout the other Saxon books. So it may seem a little odd if you've not had Saxon before, and I do want to point it out to you because I've had students before ask me questions and say, what does this odd looking N or this weird looking Z or an unusual looking R, what does that stand for? So I want to draw your attention to page 476. Make sure you take the time to go through these because that's going to help you know. One thing that's really important in Algebra 1 as well as Algebra 2 is domain and range. And sometimes they'll put domain equals and they'll put that odd looking R. What does that mean? Well, it means that the domain, the X inputs, are all real numbers. So you need to know that that R that has like 2 extra lines at the front of the R, that means real numbers. An odd looking N means all natural or counting numbers, and that would just be 1, 2, 3. If I say count for me, 1, 2, 3, that's how we do our natural or counting numbers. Whole numbers also include the number 0 because whole numbers don't have any negative, just 0 and then all the natural or counting numbers. So that's the difference between natural and whole numbers. And don't forget, integers are positive and negative, but there's no fractions, no decimals. So Saxon denotes that with the odd looking Z with the 2 lines in the middle. That's on page 476. All right, rational numbers are with a Q. So remember, a rational number can be written as a decimal, as a fraction. A good way to remember what is rational is to know what's not rational. So an irrational number would be an imperfect square root. Like square root of 4 is a perfect square root, therefore it's rational because it can be written as a fraction, right? Square root of 4 is 2. 2 is a whole number, so therefore it is rational. But if I said square root of 3, because that's not a perfect square root, that would be an irrational number, right? Your book, Saxon denotes the letter P as irrational numbers. So it's important to know that R, we've already talked about real numbers, and then the C, it denotes it as complex numbers. So that's important to understand how they notate things, because that will carry through. And those of you who are going on to Saxon Advanced Math, or some of you may be taking Saxon Geometry, you're going to see some of these notations, and it's important to know, oh, that's what they mean. Thankfully, Saxon also has a back of the book, a glossary, so sometimes if you get stuck, you can look back there and see. Saxon Algebra 1 also has formula charts, so some of that is built in there as well. Page 477 talks about set notation. It says, the use of set builder notation allows us to describe a set completely and exactly. So and it talks about that because it's so precise to know exactly what we're talking about, that really appeals to mathematicians, especially in upper level math courses that I know you guys are excited about, right? So it says the first component is the leading half of the set of braces, or the open brace. This is read as the set whose members are. And that's important to know what you're looking at and how to read it if you're looking at that. So the second component is a statement about the variable and is followed by the third component, a vertical line that is read such that. This is followed by one or more restrictions on the variable, and the last component is the terminal half of the set of braces, or the closed brace. So they give you an example on page 477, and so it shows you all of that set, and what they're wanting you to understand is how that would be read. A is the set whose members, x, are the integers, such that x plus 2 is greater than 4. Previously in the book, we would have described this set by writing x plus 2 is greater than 4, and then D, domain, equals integers. So they're just showing you a more compact way to explain what that means. So it's important. Now, when we graph it, don't forget that because we've limited the domain to just integers, it can't be a decimal, can't be a fraction, then you can see on the number line, the graph of that is just 3, 4, 5, 6, 7. It can't be 4.5. It can't be 6.2. It can't be those because we've limited the domain by saying it has to be an integer. So that's why we don't put an arrow, we don't put, just a solid line pointing one direction. We know that it has to be an integer just because the domain has limited it. All right, so now they've given you one more example, and that's on page 477. And it says to graph the set X and Y, and it's very important that we understand what that means. This is read, the set whose members are ordered pairs of X and Y, where X and Y are real numbers such that Y is greater than X plus 2 and Y is less than negative X. Previously, this problem would have been stated, and it would have written the two linear graphs, and notice that they're inequalities, and the domain are real numbers. So it's just another way to write it. And different curriculums set them up different ways. And this is important for you guys to know what this terminology means, because you might be taking a standardized test. And if you're only limited to the curriculum you use and you're seeing it worded a different way on a standardized test, it could be overwhelming. It could make you think, I've never had it written this way before. So I appreciate that Saxon is introducing us to other mathematical ways that this can be written to denote the same thing. So it's important to know what that means. So notice that they have graphed those. Notice on the bottom of page 477, the graph of this. So we're looking at our examples, and it's given us the linear inequalities, and then we have to graph those. And then notice that there'll be shading that take place, and the solution is where those shadings overlap, what's in common. Now, I do want to draw your attention to the fact that the lines are both dotted because they're not, the inequality is not greater than or equal to, it's just greater than and less than. So that's why both are dotted lines. And then where those two share is written there. Now, I do also want to remind you that you can plug these into your graphing calculator. And we've talked about that in class before, how that the greater than symbol, the triangle's at the top, the less than symbol, the triangle's at the bottom. The one thing you'll need to always verify is whether the lines are solid or dotted. And that is important if you're taking a standardized test. Sometimes they'll mix them up. So you can very quickly go through 4 or 5 options just by looking whether the line should be solid or dotted. So that will help you there. Okay, so that is lesson 117. And I want to draw your attention. There is one practice problem on lesson 117. Okay, and that is at the very bottom of this same page that we've been discussing. So let's take a look at that practice problem. So it asks us to graph the set where X, all of its members, and notice it has a Z, so all of its members have to be integers. So again, it's limiting our domain and saying that the domain can only be integers. So no fractions, no decimals, because they are integers, right? Now it says such that X plus 3 is greater than 5. Well, let's solve that. Let's go to our board, please. All right, so again, this is lesson 117. All right, and it says X, let me make sure I write that correctly, X plus 3 is greater than 5. Now remember, we know that our domain is integers, all right, because that's what the set built for us, and so we know it's limited to those integers. Now let's solve it. So if I'm getting my variable by itself, I'm going to subtract 3. So X is greater than 2. So when I graph this, if I have 0, 1, 2, 3, 4, 5, 6. Now, if I was not limited by the domain, I would come down here and put an open dot at 2 and draw my line this way. Now, the reason I cannot do that is because my set limited my outputs, right? Because it told me it can't be a fraction. Now, it said it has to be greater than 2, but it cannot be 2. Therefore, I just write that my solutions can be 3, 4, 5, 6, and I'm going to draw that arrow for that way I know I can continue going in that pattern, but it cannot be a decimal or a fraction. So my solution is X can be 3, 4, 5, 6, and continuing. So it cannot be because my set that was built notated that it was only integers. So that's very important to be on the lookout. So that's all that lesson 117 is going over for us today. All right, let's move ahead and we'll go to the next lesson, lesson 118. Now, lesson 118 is logarithmic equations. And I'll give you a moment to turn your page because we're skipping through the lesson problems so you can do those at home alone, okay? Page 479 starts the logarithmic equations, all right? So how do those work? Well, we've already discussed logarithms. Now we're stepping into equations. So equations, don't forget, we always have a cute little way to remember that. An equation has an equal sign, right? So just like that's true in previous Algebra 1, that's true with logarithms. So now we have an equal sign. Now, your book talks to us about a couple of facts we want to make sure that we review before we jump into the new material. So your book reminds you that we have been working with logarithms, and it says, a reminder in bold on page 479, if the bases are the same and the logarithms are equal, the numbers are equal. Now, I know that might not mean much to you now, but basically they're putting in bold, hey, this is a shortcut. I love shortcuts. I hope you guys do too. Shortcuts aren't I would never encourage being lazy in math, but you know, that whole using your time wisely. So anytime you can find an easier way, it's kind of like a pulley system, right? You could carry, if you were a contractor and you had to go up 6 flights of steps, you could carry every piece of material up, or if you found a pulley system, that might be wiser work, right? Because it's faster, but you're still getting the job done. So I'm not encouraging not doing your best. I'm just saying that if there's a quicker way to get to the answer, we love those, right? All right, so look at the next. It says here the bases are both 7 and the exponents are equal. So the number on the left, which is 49, equals the number on the right, which is also 49. So your book is showing you log to the base 7 of x equals log to the base 7 of y. If both bases are 7 and the equal sign tells us that the logarithms are equal, so the arguments must be equal. This means that x equals y. So we would write, so we can write it that way. So that's very important to know that if the bases are the same, then it means that they are equal. Now, your book shows the next. So it says, look, if I have log to the base 5, notice I'm on the bottom of page 479, and it says log to the base 5, and in parentheses it has x plus 4 equals log to the base 5, 7. So if the bases are the same and the equal sign tells us the logarithms are equal, so the argument must be equal. So what does that mean? Well, friends, my bases were the same because they were both log to the base 5. So I can simply take that out and then just write x plus 4 equals 7. So this is where the shortcut part comes in. We love that. So since the bases are the same, we write it. So we can solve x plus 4 equals 7 by subtracting 4 to both sides. X equals 3. Problem solved. So we love that. That is great. All right. Now, your book also, there's several places where it's in bold on lesson 118, and I think it's very important to take the time to go over that. All right. Now, it also points out on page 480, remember that we can multiply numbers by adding their logarithms. So remember when the bases were the same, your book shows 10 raised to the second power, or 10 squared, times 10 cubed, because both of the bases were the same. My exponent rule says if my base is the same, then I add the exponents. 2 plus 3 is 5. Now, it says to use this rule backwards, we note that if the bases are the same and the logarithms are added, then the arguments are multiplied. So one thing I want to draw to your attention is that logarithms are another way to write exponents. And so when you nail that down, you can go back and forth between those two problems to more easily solve what you're looking for. So they showed that if I say log to the base 10 of 5 plus log to the base 10 of 7 has the same value of log to the base 10 5 times 7. So I want to draw your attention to this fact, because before we would say 10 squared times 10 cubed equals 10 to the 5th. We added them because remember that when I'm multiplying, the step before is adding. Well, with logarithms, if I'm adding them, we look at the step after, and that would be multiplication. So that's why that's so important to be able to understand that I multiply, so I can go back and forth between the two of these, because I understand that logarithms are an extension of exponents. So just like we looked before, what was the step before? Now, if we're adding logarithms, we know the step after is the same thing because logarithms were one step behind. So I hope that that makes sense to you at home as you look over page 480. Okay? All right, I'm going to move this just a little bit. Sorry. All right, y'all can tell I'm no professional, right? All right, so let's take a look at the next part. So they're also pointing out to you that the same is true with division. So division has to do with if my bases are the same, I subtract. So if you see a logarithm that's subtracting, then we understand the step after subtraction would be division. So they show you log to the base 3 of 14 minus log to the base 3 of 9 has the same value of log to the base 3, 14 over 19. Because it was subtracting, the step after subtraction would be division. So as before we're always taking one step before, now we'll be looking what's one step after, because we're doing the inverse there. All right. Now, it also pointed out to you the exponent rule, that if I have a base raised to the power, and then I'm taking that and raising that to a power, the step before would be multiply. So to use this rule backwards, if you see a logarithm that's being multiplied, the argument is raised to that power. So to illustrate that, they show 10 squared equals 100. So the logarithm of 100 to the base 10 is squared. If we multiply 4 by the logarithm 2, we have raised the number 100 to the 4th power. So they're showing that. So I just multiply there. And that's what your book is showing you, because if I have 10 squared, that is 100. and then 100 raised to the fourth power. So we're right in the middle on page 480, and they're just showing you how you can go the step after or the step before, and they're showing different ways, different shortcuts to see that, okay? Now, so it also shows in the language of logarithms, we can write. So I'm on the about 2/3 of the way down on page 480. I hope you're following along at home, because I think going through these examples, especially the boldface, is going to be a great help to you. So it says 4, and that 4 is in front of the logarithm. 4 times log base 10 of 100 means log base 10 of 100 raised to the fourth power. So if you see a number in front of a logarithm, you can convert that to the exponent after, because remember we said that if I'm multiplying, that's raised to the power. The step before is multiply. So the step after multiply would be raised to the power. So we're moving back and forth between those, and I hope that that makes sense to you. Let me write that on the board. So again, we're on lesson 118, and we're talking about how in logarithms, if I'm raising to a power, the step before is multiply. If I'm multiplying, the step before is adding. But since I'm doing logarithms, I might need to go the step after raising to a power if it were multiplied. Like we just talked about, 4 in front of the logarithm, right, would be raising this to the power of. So you're moving back and forth between those two. So I hope that that makes sense to you, that just like before when we were talking about the exponent rule, it's always one step behind. Now when I'm taking logarithms, I'm going to go to the step after. So it's the inverse of each other. Logarithms are another way to write exponents. All right, so it says the coefficient of a logarithm can be turned into an exponent. And they give an example in bold on the bottom of page 480. 4 times log to the base 3 of 5 can also be written log base 3 of 5 raised to the fourth power. We took that 4 in front and it became the exponent. So that's important. An exponent can also be turned into a coefficient. So there are going to be certain times that it's easier to go back and forth between one or the other, because sometimes it'll be easier to have the logarithm, sometimes it'll be easier to have the exponent. So it just depends on the problem, and of course we want to make sure we're using our time efficiently, right? So log to the base 3 of 5 raised to the fourth power can also be written 4 times log to the base 3 of 5. All right, so then they're showing different examples there. Now, look at the very bottom of page 480, and then the solution is at the top of page 481. So solve log base 3 of x plus 7 plus log base 3 of 2 equals log base 3 of 20. Now, it says begin by noting that we have never used base 3 for computation with logarithms. Authors of mathematics books like to vary their algebra of logarithmic problems by using unusual bases. The unusual base tells us that this is probably a problem about the algebra of logarithms. We note that the logs of x plus 7 and 2 are added so that x plus 7 and 2 are multiplied. So one thing I want to point out to you is typically you're going to see the most common log base is 10. So if you see something to an unusual base, they're just wanting to point out to you the algebra. So that's what Saxon's pointing out to you, is when you see it in standardized testing, we understand that the most common is going to be log to the base 10. Now, because all of these were log base 3 of all of them, we want to point out that notice that it was log base 3 plus another log base 3. So when I'm looking at my plus sign, after plus would be multiply. So since they're all in the same logarithm, I can say log base 3, and it's being multiplied x plus 7 times 2. I'm multiplying it because before I was adding. I'm doing the step after this time. Equals log base 3 of 20. Now, I'm going to distribute my 2 to both, and because all of it is set up in the same logarithm, I can take out the logs and set them equal to each other. X plus 7 in parentheses multiplied by 2 has to be distributed equals 20. So I'm just going to solve it. So that was a much more difficult problem, but when I understand, hey, if my logarithms are the same base, just set everything equal to each other. And don't forget, you're doing the inverse. You're doing the step after, whereas before with our exponents, we were doing the step before. Now we're doing the step after, right? Now, look at the next example on page 481. It says log to the base 14. All right, we don't use that much, do we? Now, it's log base 14 of x plus 3 minus. Now, I have to think through, if I have minus right here, what would be the step after minus? The step after plus was multiply, so this would be, you guessed it, divide. So we're looking at the step after because we're using logarithms, right? So it says log to the base 14 of x plus 3 minus log base 14 of x minus 3. So that's going to be divide. Since it's being subtracted, I'm going to divide it, equals the log base 14. Again, all the log base 14s are set equal to each other. So that's going to be equals 7. So that's how I set it up, right? So now it says the bases are equal, so the logarithms are equal. So I can then solve it. How do I solve this? Well, I'm going to have to get rid of the denominator, so I can multiply both sides by x minus 3 to get rid of the denominator there, or I can just remember the cross products always equal each other. So I can just do 7 times x minus 3 equals x plus 3. And I can distribute that and then solve. And your book did all that, so I'm not going to take the time to go down through. But I do want to point that out to you all, that as you solve it, you'll get it down to combine your variables together, and you'll end up, your book shows there how to solve it, x equals 4. All right, they give one more example there, and this one I don't want to skip because it has a coefficient in front, so I want to talk about what do I do with that, right? So let's look at the bottom of page 481, and it says 3 times log base b of x equals log base b of 64. Now we look at that and we think, wow, that's different than how I've seen it written before. But let's not let that overwhelm us, because there's a variable in the front, and it has, not a variable, a coefficient. So it's 3 times the log of base b of x equals log base b of 64. So my log base b are the same, but this 3 means that I can write it log base b of x cubed, because remember the step after multiply would be raised to a power, right? Equals log base b of 64. Now because my logarithms are set to the same base, I can just say x cubed equals 64. Then I'm going to cube root both sides. So what is x? What does x equal? If I'm looking for the cube root of 64, plug that in your calculator. Cube root of 64 is 4. 4 times 4 is 16. 16 times 4 is 64. So that's how I solve those. Now we've got 3 practice problems I'd like to take the time to go over now with you. We've gone through the whole lesson of lesson 118, and I'd like to take the time to go through those practice problems together. All right, so lesson 118, and we're looking at practice A. All right, so practice A is on the bottom of page 481, and I apologize, I'm stepping in and out of the screen there, so I apologize. So I've got log base 5 of x plus 8 plus log base 5, let me move that lesson number so we're on 118 up here, log base 5 of 4 equals log base 5 of 80. All right, when you look at that, do you think at first, whoa, that is a lot of information? All right, so we've not we've not dealt before with logarithms written in these type of equations. So when I first look at it, it can be very intimidating. So don't allow that to intimidate you. Let's think through. If I'm adding, the step after addition is multiply. So what does that mean? Log base 5 of x plus 8. Since I'm adding, I'm going to multiply. Times 4 equals log base 5 of 80. Now, because my log base 5 are set equal to each other, x plus 8 times 4 equals 80. Now I'm going to distribute that 4 to both, so it'd be 4x plus 32 equals 80. Now I'm going to solve that, and I'd love for you guys to solve that at home as well. So I'm going to subtract 32. So 4x equals 48, because I borrowed from the 8. Got 7, so that'd be 48. Divide through by 4. So therefore x has to equal 12. So that's our practice A. So I hope that makes sense to you, why the step after addition is multiply. So that's why I solved it. And because they were set in the same logarithm, I can set them equal to each other. Not too bad, huh? All right, let's jump into B. All right, so we've got 2 more practice problems to solve together. So let's look at B. All right, log base, the practice for our logarithmic equations. So I'm looking at B, and it says log base 7 of x plus 7. Oh, I wish we were in class and you all could call these out to me, right? Minus log base